Hi everybody, welcome to this third part in a series of lectures on Boolean formulas and equations. And we are actually looking at some new material that pertains to formulas containing quantifiers. So we've discussed existential quantification, which is the sort of backwards looking E, and also universal quantification, which is the upside down A. And we've also discussed various ways to represent propositions and to group propositions into predicates, and that we have this concept of bound variables, which can assume any value from what is termed a universe of discourse. And we've looked at natural numbers, and the natural numbers are the integers, sometimes excluding 0, and the positive integers, that is. And there's some one sort of thing that's covered in this reading from P&G is that you can basically reason with a given universe of discourse, and that the reasoning is actually independent of the universe of discourse, and that's something to keep in mind. So as we've seen, the quantifiers, the universal quantifier, which is the upside down A, and also the backwards E, which is the existential quantifier. These quantifiers provide a way to convert predicates into propositions. And we have been reasoning about Boolean formulas constructed with propositions and operators. And we're going to take a look at some new methods and equations to make the same kind of reasoning possible with formulas containing quantifiers. So we want to extend some of the earlier work we looked at in writing proofs about Boolean equations, and we'd like to do the same with formulas containing quantifiers. However, as we'll see, there's actually a four-step process that we have to apply in order to be able to prove Boolean formula containing quantifiers is either true or false. So we can let P of x, y denote the proposition in the predicate P that is indexed by the pair x and y, where x comes from the universe of discourse for the first index and y from the universe of discourse for the second index. And for now, let's assume the universe of discourse is the natural numbers. And to recap, these are the positive integers, sometimes including 0. And that's something we talked about a couple moments ago. And we can say that P5 of 2, P0, 6, and P3, 7 are specific propositions in the predicate P. And what we cover on reasoning with quantified predicates applies to universe of discourse other than the natural numbers. And that's a pretty important realization about this process of constructing proofs about Boolean equations containing quantifiers. And we can replace a variable by any formula representing a value in the universe of discourse. For example, we might assert that if x and y represent natural numbers, then P5, 2x plus y plus 4 is true. And if we consider the existential quantification, which is given here, we are assuming that for some x, P of 5x is true. And this formula has the value of true if there is at least one value for x that results in the proposition being true. All that's required is one occurrence. It could, however, be more. As we have seen, equations may contain variables. It is also possible for equations to contain constants. Make sure to explicitly state when one is working with a constant. There may be multiple constants. Each constant should have a unique symbol. And what was a bound variable in an existential quantification becomes a free constant in the formula that represents a particular proposition in the predicate. And this is a proposition that has the value true. It is also possible to prove equations that utilize quantifiers. One way to complete such a proof is to systematically remove quantifiers. And once the quantifiers are removed, we are left with a formula without variables, such as P53 or P5x0, where x0 stands for a particular element in the universe of discourse whose value we don't know, but which in any case stands for just one value and cannot be replaced by another variable or formula. And once the quantifiers have been systematically removed, we are left with a Boolean formula for an ordinary proposition that can be proved using the same methods utilized with Boolean propositions as we were looking at earlier in this chapter. And so we have a 4-step strategy for reasoning with quantifiers. Step 1, we rename bound variables. Step 2, we migrate quantifiers to the front. Step 3, we eliminate quantifiers, leaving a proposition. And step 4, we prove theorem about the proposition. And step 4 is the familiar proof of a Boolean proposition, which we've already covered. However, steps 1, 2, and 3 are actually new. So renaming bound variables, which is the first step to take when reasoning with quantifiers, is sometimes necessary to prevent a quantifier from accidentally referring to a different bound variable that happens to have the same name. So if we consider the following formula for all x odd x, or for all x even x, and these methods, odd and even, which are, I guess, in fact, predicates. These predicates essentially return true if the argument is an odd number in the case of odd, and even returns true if x is even, and x is the value that's passed in. So the universe of discourse for both of these quantifiers is the integers, and this formula is false because there are two distinct quantifiers. There are values for which both the left-hand and right-hand operands are false, and there are two bound variables in this formula. The variable x is utilized as a distinct bound variable in each quantification. So the difficulty here is that we can simultaneously pick a value for x in the left-hand operand, which is false. We can also simultaneously pick a value for x over here, which causes this proposition even x to also be false. And of course, false or false is false, and that's why this expression is false. And we could also slightly revise the formula we looked at on the previous slide. We could say for all x, odd x, or even x. And in this case, this works because, as we know, the universe of discourse of integers, in that universe of discourse, there are only two possible types of values. We have either an odd integer or an even integer. And so one or the other will be true. And since we're using this logical OR to connect this call to odd and this call to even, that we're guaranteed that either the left-hand operand odd or the right-hand operand even is going to be true. And if one is false, then the other is bound to be true, and the same is true the other way around as well. And while similar to the formula we just previously examined, since there is a single quantification, this formula has a single bound variable and thus evaluates the true. And the name one picks for a variable has no impact on what the variable represents. Picking different names for bound variables prevents confusion, and each bound variable in a quantified equation must be assigned a unique name. And recall that there are two different but identically named bound variables in the following formula. And this is problematic. This expression, of course, is false, but if we look at the way we revised it up here, this is, of course, acceptable and evaluates the true. And we can also sometimes distinguish variables in situations in which there's ambiguity, or there's a possibility for variables to be confused. As long as we're systematic about the way we rename variables, we can then resolve ambiguity or the potential for confusion. So you can see here if the first quantified variable x is specified as x, and if the second quantified variable is specified as y, there's no confusion. And then alternatively, we could call this the first quantified variable y and the second quantified variable x, and this enables us to prevent the possibility of confusing variables in Boolean expressions containing quantifiers. It prevents confusing variables that appear to have the same name but in fact are distinct. And so going back to the reading, there's an equation in the reading, and it's actually given right here. You can see it. We would like to prove this implication, and you can see that this quantified predicate has two indexes, x and y. And actually the first thing that we're going to do is rename two of these variables to prevent the possibility of confusing them. So this formula actually has four different bound variables, but only two names. And so what we do is rename two of them to avoid conflicts. And you can see that's what we've done here. Before the equal sign, this is our original formula, and you can see we have both x and y as bound variables in the left-hand operand of this implication, and also in the right-hand operand of this implication. And then to the right of the equal sign, you can see we've renamed y to v. And then if you follow along in the second equation, we're taking the result of the first equation, and we're further transforming it by renaming x to u. And you can see to the right of this equal sign here, we have our final equation in which y and x in the left-hand operand have been renamed to v and u. And there are now four variables in the formula we would like to prove: u, v, x, and y. So each of these equations, in each of these equations that we've seen, it's important to remember that x must not be a free variable in Q or in Py, and y must not be a free variable in Px. If it's the case that these any of these either of these variables x or y occur as free variables, when we perform the migration from the left-hand side of the equal sign to the right-hand side of the equal sign, there will actually be a change in the meaning of the equation. So you have to make sure that when working with quantified predicates, when variables are renamed, it's important to keep these rules in mind. So the next step is to migrate the quantifiers to the front of the formula so that we can end up with something like this. So you can see we have universal x, universal v, existential u, and existential y. And then right here inside, nested up in the middle of this, or all the way to the right of it, almost all the way to the right of it, we have our implication. And the equations detailed in the following 3 slides provide the basis for quantifier migration. And applying these equations in a proof calls for a close look at parentheses to be sure that the cited equations matches the syntax of the formula that is under scrutiny. And migrating quantifiers is a tedious process and requires careful attention to detail. So here in the next 3 slides, we're looking at basically defining transformations. So on the left-hand side of the equal sign in each of these equations, you can see that we're able to transform expressions which have the same form as these equations at the left of the equal sign with these equations that occur at the right-hand side of the equal sign. And we have both universal and, existential or, universal or, existential or. And you can see that there's a difference in the scope of the quantifier once the transformation is complete. And using these equations as the basis for transformations that are performed upon equations containing quantifiers, we can use these equivalencies as a way to facilitate migrating quantifiers to the front of equations with quantifiers. And then, of course, that isn't, our primary goal. Our primary goal is to not only migrate the quantifiers to the front, but also to eliminate the quantifiers, and then to be able to prove the underlying Boolean formula as either true or false. And so these equations that we're utilizing for reasoning with quantifiers are, these equations are essential. They're indispensable for being able to transform equations containing quantifiers into simpler forms with the, secondary goal of migrating the quantifiers to the front, and the primary goal of eliminating the quantifiers and proving the underlying Boolean formula. And so here in slide 2 of 3, detailing equations of quantifier reasoning, we have universal implication, we have existential implication, we have implication universal, and we also have implication existential. And you can see, if you examine the equations on the left-hand side over here of these equal signs, you can see that we can perform transformation going from left to right, and with the explicit goal of getting the quantifier right at the front of the equation. And this actually simplifies the next step. Well, I guess it makes the next step possible. And the next step, of course, is to eliminate quantifiers. And these equations here in slide 2 of 3, detailing these equations of quantifier reasoning, you can see that we can simplify equations containing quantifiers and also implication as well, which is this arrow pointing to the right. That's referred to as an implication. And we've kind of covered implication before, so it's not something new here, but it still may be new in concept. And one important thing to keep in mind about implication is there's only one situation in which an implication is going to result in false, and that's when the left-hand operand of the implication is true and the right-hand operand is false. And that's the only possibility out of all 4 possibilities of an implication in which the implication is false. And here in the third slide, you can see we have not universal and we have not existential. And we're basically bringing the quantifier to the front again. And this simplifies the next step. And the next step, of course, is to remove the quantifiers. We also have the renaming of universal. We have the renaming of existential. And you can see we can rename, for all x, for all y. And we can also rename for some x, for some y. Oh, this is actually a proof of one of the transformations we just looked at on the previous 3 slides. And this is universal implication. And you can see that we're starting with for all x, p of x implies q. And of course, initially, the q is outside the scope of the quantifier. Then by implication, we can transform the implication into a logical OR. And we've also negated for all x, p of x, px. And in the second step here, we've applied not universal. And this enables us to bring the not into the middle here, right up against our predicate. And then we also have for, I guess this is existential OR. Which enables us to bring this universal or this existential quantifier of x even out further, outside the scope of the logical OR. And then we apply implication a second time, and we end up with what we sought to prove, that this equation up here is equivalent to this equation down here, and that is effectively the transformation that we sought to perform, which brings the quantifier right out at the front of the quantified equation. So we were working on transforming the formula on the right-hand side of the following equation into the left-hand side. And you can see here we start out with what we're given for some y for all x. Pxy implies for all x for some y, pxy. And we transform this into the equation that appears here to the right of the equal sign. And we renamed y and x in the left-hand operand to v and u. And we accomplished this by utilizing rename existential and also rename universal. And in the following slide, we're going to take a look at how to complete the migration of quantifiers. So you can see by applying these the equations that we just previously looked at, we're able to transform this equation at the top into this equation down here at the bottom. And of course, when we start out, the quantifiers are dispersed throughout the equation. And our goal is to bring the quantifiers all the way to the front of the equation, and then to leave the Boolean part of the quantified equation right nestled in right up against all these right parentheses you can see down here at the right. And we're just using the transformations that we looked at, those, I believe, 12 transformations that we looked at in order to bring the quantifiers all the way out to the left over here of this equation. And so we apply, first we apply imply universal, then we apply existential imply, then we apply universal implication, then we apply implication existential. And you can see by applying these transformations, we are able to bring the quantifiers out in front. And again, I just want to emphasize that performing these transformations requires quite a bit of work to get it just right. But I think you'll find if you work through the examples in the book that with a little bit of effort, it isn't difficult to see how to put these formulas containing quantifiers together. So after we end up with this equation down at the bottom here, in which the Boolean part of the quantified equation is nestled right in here tight against all these right parentheses, we can actually perform some additional work following the four-step process we examined a bit earlier in these slides. we can actually remove the leading universal quantifications for both x and v, replacing occurrences of both x and v with x0 and v0 respectively. And regardless of the values these renamed variables assume, the truth value of the formula remains unchanged. And this results in the following formula, in which we've named we've named v v0, and we've named x x0. And you can see now we only have two leading quantifiers, existential u and also existential y. And since y comes from the same universe of discourse as x0, since u comes from the same universe of discourse as x0, and y comes from the same universe of discourse as v0, we can actually set u equal to x0 and y equal to v0, and this results in the following formula. P x0 v0 implies p x0 v0, and this is actually an ordinary Boolean proposition, and the self-implication axiom shows that this formula has the value of true. And this axiom appears in figure 2.11 on page 29 in P&G.